Hello again. We're still working on equilibrium systems and different ways to look at them, and here's another way to look at them. What we have here is a plot of the concentrations of three species in a reaction, and let's get the reaction down. They say this is ammonia forming from its elements. So we are making ammonia, which is NH3. Ammonia is made of nitrogen and hydrogen, and I don't remember if we need this balanced, but let's be good boys and girls and balance it. Two nitrogens means we need a two there. This is six hydrogens, so we need three there, and you don't have to write a one for the nitrogen, but you can. So there's our balanced reaction. And yeah, okay, so this shows we have three plots, and one of them here is open white circles. That's our nitrogen. So this shows we started with a certain amount of nitrogen, and then the amount dropped. Why? Because the reaction's using it up. And the black dots are hydrogen. Again, we started with some roughly 7 moles per liter of hydrogen, and then that amount dropped as we used it up. And we started with some low amount of ammonia, and then that amount went up. Why? Because the reaction's making it. And these amounts changed fast at first, and then they slowed down, and then they hardly moved at all. And then they settled down and went flat because somewhere around here the system said, good, I'm at equilibrium, I can relax now. And it just settled into a dynamic equilibrium where the numbers didn't change anymore. And we know that these systems always try to do that. They react until they're happy and their reaction ratio equals KEQ, and then they just sit there for all time. So, what do they want with this? Write and balance the reaction for ammonia. Okay, well, I did that without even knowing it was the first question. That's just a good idea when you're studying a system, is write down the reaction and make sure you understand it. So here is ammonia being formed. At what time did this system reach equilibrium? That means when did these curves flatten out? Dropping, 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 dropping just a bit. Let's say it's flat there. And all of these go flat at the same time because when the reaction stops, it stops for everybody. I would say around here, around there, so around 20 minutes is when the system hit equilibrium and the numbers stopped shifting. Calculate the equilibrium constant. You remember how to do that? If you want to find your reaction ratio, it's the products over the reactants, and our only product is ammonia. And this coefficient of 2 means power of 2. For reactants, we have nitrogen. Coefficient of 1, you can put a power of 1 on here if you want to. It's not mathematically necessary. And our other reactant is hydrogen. And coefficient of 3 means power of 3 here. So that's our reaction ratio, and if we want to find KEQ, we need some equilibrium numbers to put into this. Now, these are not equilibrium numbers. These are initial numbers. So don't read those, and don't read here either. It's not at equilibrium yet. Not there, not there, not there. As long as these things are moving and changing, you're not at equilibrium. So you're at equilibrium when you get to here. Those are the values we want to read to calculate KEQ. And this is not the friendliest graph to read those off of, but we will do our best. When we're at equilibrium, actually we need nitrogen, or ammonia first, sorry. Our ammonia number is, is that 4.2, 4.3? If I had a ruler and drew some grid lines, I could maybe do a better job of this. I'm going to say it's 4.3. If you think it's 4.2, you're not crazy. I'm honestly not sure. But let's go with 4.3 just to get a calculation done. And we square that. And now we need the nitrogen concentration. That's this curve. And when it flattens out, we are at line. 8.3, 8.4, I'll say 8.3. When humans reading graphs like this that don't have a lot of grid lines is a little rough, as you can tell. Do your best, that's all we can ask. Hydrogen, this curve. Try to keep that flat. 5.8. I feel reasonably good about 5.8. Let's go with that. 5.8, and don't forget your power of 3. Okay, find calculator on desk. Key numbers into calculator. 4.3 squared divided by 8.3, also divided by 5.8 to the third, and I get 0.0114176 for the equilibrium constant. Now, talking about precision a bit, I wrote these numbers to 2 significant digits, but you heard me talking. I was never sure for any of these about even the second digit. So if we were really being rigorous here, we shouldn't report this answer to 2 significant digits because these numbers are not very solid. This is 4 point something, 8 point something, and 5 point something. So it would be honest of us to say, look, I'm only sure about 1 significant digit here, and so I'm only going to say 0.01 for KEQ. That's not a very precise number, but that's because I wasn't making very precise readings on this graph. If you want more sigdigs, get a better grid that has some tick marks on it so you can more confidently read the numbers on here. That's the price of precision, if you care about that. But hopefully the setup makes sense to you, products over reactants and reading numbers off of the curve. This is stuff we can ask you to do. And I think there's one more question at the very bottom here. Does this system favor the products or the reactants? You can't really eyeball that off of these curves, or at least I can't. I've never been good at it, but good news, you don't need to. Just look at your K. Do you remember the rule? If K is big, as in bigger than 1, then your system favors the right side or favors the products. And in this case, where your K is smaller than 1, your system favors the reactants or the left side. Good. See you in the next one.